Today, I am excited to introduce you a fundamental theorem of algebra. I divided the introduce three parts. The first is history of the theorem, and the second is explanation of the theorem, and last is application of the theorem. So let's continue to the first part, history of the theorem. First is the purpose. In ancient times, people gradually derived the concept of algebraic fundamental theorems by studying the number of solutions to high-order equations. In the 16th century, both Peter Ross and Albert Girard proposed similar concepts in their books. Afterwards, famous mathematicians such as Euler and Lagrange attempted to prove this theorem, but all ended in failure. And then, until 1799, Gauss rigorously proved this theorem for the first time, using the content of topology to prove it. Afterwards, he also provided three additional proof methods. And this theorem was increasingly mentioned. And it is the second part, explanation of the theorem. Fundamental theorem of algebra. Let Pg like this formula, Pg equal to a and c n plus a n minus 1 c n minus 1 plus 1 a1 z and plus a0 be a polynomial of degree n with coefficients in c. Then the polynomial equations Pg equal to 0 has a root in c. We can think it of as like Pg equal to x minus c times qz. It holds true in all cases. And then from this one, we can get the corollaries. And then we can get a corollary. Let Pg like this formula be a polynomial of degree n with coefficients in c. Then the polynomial equations Pg equals to 0 has n roots in c, containing multiplicity. And we can think it as Pg equal to x minus c qz, and the degree of it is minus 1. And also we can factor qz like qz equal to x minus c2 and times like rz, and we can do it n times. So this formula has n roots in c. Yeah, and we can get this. And then I want to introduce something of its proofs. There are many ways to prove this theorem, all of which involve some mathematical analysis, at least the concept of continuity of real or complex functions. Some proof also use differentiable functions, even analytic functions, due to the fact that the proof process involves many theorems that we have not learned before. We will not elaborate on them in detail here. And then we move on to the next part, application of the theorem. So the first, and I think the most important part of the application is solving polynomial equations, guaranteeing the existence of roots. The fundamental theorem of algebra guarantees that every non-constant polynomial with complex coefficients has at least one complex root. This is crucial for numerical method and symbolic computation. For example, resolving higher degree polynomials, we know that there is at least one complex root, which provides a foundation for further analysis. Polynomial factorization. The fundamental theorem of algebra also states that every polynomial can be factored into linear or quadratic factors with real coefficients. This is useful for simplifying algebraic expressions and understanding the properties of polynomials. And the second part of the application is mathematical physics, quantum mechanics. In quantum mechanics, many physical problems such as the energy levels of particles can be represented by solving algebraic equations. The fundamental theorem of algebra guarantees the existence of roots for these equations, which is necessary for modeling physical phenomena. Wave equations. Many wave equations for sound or light waves in physics are described by polynomial equations. A fundamental theorem of algebra ensures the existence of solutions to these equations, which helps in solving complex physical problems. And the last part is control theory and signal processing. Stability analysis. In control theory, the roots of polynomial equations such as the eigenvalues of a system are crucial for determining the stability of the dynamic systems. The fundamental theorem of algebra ensures that polynomial equations have roots which can be analyzed to assess whether the system is stable by checking if the real parts of eigenvalues are negative. Filter design. In signal processing, the frequency response of filters can often be expressed as polynomial. The fundamental theorem of algebra helps in analyzing poles and zeros of filters, which is essential of optimizing their performance. Yeah, that's all I introduce. Thank you listening so much.